All right, so, oh, awesome, nice and fast. So, like Adam said, I'm Alex, and yes, I do work at Apple now, but I have been told by, as you can guess, a pretty scary looking legal team to make it very, very, very clear that none of this comes from what I've done since I've joined Apple. I came up with this talk, I presented it while I was at my last job, actually. I did iOS stuff for a few years at a company called Flip. So all of what you're about to hear now is done with just publicly available UIKit APIs and documentation. So with that out of the way, nice little disclaimer. To really drive home that point for the next 45 minutes, you're not only going to see light mode slides, you're also going to see serif fonts. So just really visual reinforcement here. But the other burning question aside from all that is probably why? Why on earth would anyone ever want to talk about something so nerdy and tedious as 3D transforms? And the answer is simultaneously what you might not expect and also probably deep down something that we've all run into, I'm sure, no matter how limited our indie or professional iOS experience might be. And at this point, it'll become really clear that this has nothing to do with Apple because the answer to this question, it's Xcode. This goes back to when I was an intern, and don't get me wrong, I feel so lucky to have been given and to continue to get development hardware. You know, working for a company and being blessed enough for them to supply me with a laptop and a phone. It's an amazing experience. I know for a lot of us, and I've been there, we're using an older laptop, we're using the simulator at all, and we're still grinding and getting work out there, and that's really awesome to see. But having said that, when I was an intern, you kind of get like, oh, there's a laptop lying around, you get like an old, really, really old like i5 with like 8 gigs of RAM. Here, have fun compiling our app. And for those of the more seasoned iOS developers out there in the room today, you might feel the pain here. At that point in time, our project had CocoaPod, Carthage, Swift Package Manager, not the fun one that we know today, the early one, and manually imported frameworks, all on top of our mountain of source code with like a 3,000-line Objective-C app delegate, massive view controllers everywhere. Anyway, you get to a point where if you want to switch branches and try to compile, 15 minutes later, Xcode will tell you that it failed at the very last step of the build, you know? And that time really adds up. You spend hours of your day just trying to switch a branch. It's not fun. And you probably, I had my own little ritual, I'm sure we all do, for getting Xcode to compile in that state, you know? You clean the build folder, then you quit Xcode before it has a chance to do anything again. You don't touch anything, you clear the derived data folder. I set up a shortcut because I did it so often. I could actually say HS, clear derived data, which is pretty neat, I found. That's the only thing I used Siri for years. So you clear derived data, you open Xcode, but you're standing on one leg and you're crossing your fingers, hit the build button, throw salt over your shoulder, turn 3 circles, look into a dimly lit mirror and say, Craig, very softly. But anyway, I digress. That's just for getting it to compile, though. If you want to use some of the really awesome features that Xcode gives us, and Xcode, look, I talked crap about it for a minute there, but it is really awesome with what it provides, like the debug view hierarchy that we see here. It's awesome when it works, but for me on that hardware, it would take another like few minutes just to hook up to the app that you've got running on your screen, just for you to see like what's going on with the stack view that I made, what happened to that label, why isn't it showing up where I want it to? And I bring up this specific example because this tool and the difficulties I had getting it working, that was actually the motivation for an internal dev tool that I developed that led to this topic for today. I'll show you pieces of that dev tool throughout this presentation, and we'll put all those pieces together at the end to see how it all works in unison. I really wanted to essentially recreate this experience as best as possible in the app directly. How can I get to this point where I can see the views, move around, and maybe even navigate and see all the different properties the exact same way that you can in Xcode without needing to be hooked into a live session and bogging down both your phone and your laptop? And I know that other indie devs before me and since have probably definitely done it and done it better than me. But this is just how I went about doing it. I saw the challenge and I thought, I could figure that out, right? Famous last words. But I digress. This is how I reasoned about it and how I solved this implementation. So hopefully it helps some of you. So just a quick refresher for most of us, but if you don't know, it's totally fine as well. Pretty basic stuff here. When it comes to the iOS coordinate system, 0, 0 is the top left corner of, well, I wanted to say app screen, but we talk about scenes now, right? That's the modern way to go about it. Anyway, 0, 0 is the top left. And from there, your values will always be positive as you go further right and down on your screen. Nice and easy. And any individual point on that screen, like the very last pixel in the E in schedule, say, is some x comma y pair on the screen represented there. And it's represented in our iOS APIs usually as a CG point. Sometimes we store it ourselves. Not really important. But your UI views, your Swift UI views, are really just a collection of these points, however many it needs to render when it shows up on the screen. So that's x, y. And that works fine for the most part. We're just building simple apps with labels, like the Swift UI stack here from the SwiftLeeds app. It's pretty much fine as it is. If you needed to describe it, you could get away with just x, y. But once you start getting into the idea of building more complex layouts, like say, hey, I want an image to maybe partially overlap with the entry for registration for whatever reason, then you kind of start to need the idea of, OK, well, which one should be on the top? And that's where iOS introduces the idea of the z-axis, or as its API is known in UIKit, a view.layer.z position. And what this really is just a measure of how far in or out of the screen your view is in the app relative to the other siblings that it's around. You can totally achieve this without needing to know what the Z position is at all. In SwiftUI, say you had a Z stack, and you just declare the views in the right order. You know that the one you declared last, like it'll be on the top, right? Pretty straightforward. UIKit, you just add subviews in the right order, and the one you add last will be on the top. And that's totally fine, but if you want more fine-grained dynamic control during runtime, maybe you want to reorder things, the user tapped on something, you want to bring it to the front, the Z position unlocks that ability for you. You could set it to something like 10,000 just to ensure that no matter what happens, it'll always be brought back to the front. The easiest analogy that I can think of for this is if you're making a PowerPoint, the slide deck maybe, and you threw in 2 images from Google Images. And one of them ended up on top, and you're like, oh, shoot, that's not the one I wanted. Well, that's totally fine, because you can just right-click on one of them, send it to the back, and it just goes behind, and you're fine, and you can move on. Sending it to the back is the same here as lowering its Z position until it gets to a point where it's lower than that of its sibling, and it just gets rendered the next time around behind it. So we have that X, Y, we have a Z position, put them together, and this is kind of our starting point for the talk today. This is how we get to a 3D system on iOS. And when it comes to transforming a view, remember we just mentioned briefly that a view is really just a collection of points. So we can think of a transform under the surface as iOS applying a calculation to every point in that view. So for every point, x, y, z, when we want to obtain a new point, a, b, c, x prime, y prime, z prime, the idea is we move from one point on the screen to another. So how does that happen? And the answer to that is math. There's no fun way around saying that. I know. I hate myself as much as you just started hating me now, too. Don't worry. We're going to be doing a little bit of math today. But the break is just around the corner. I'm gasping for that coffee as much as you all are. We'll get through it. But just briefly, this is kind of off the cuff, but I kind of love how all of our talks are kind of linking together in ways that I wouldn't expect. Richie, I don't know where you're at, but what you mentioned at the start about just the idea of not letting us as devs get lost in this idea of, oh, the syntax has to be the prettiest, or like, look at how clean this code is. There's no way it could run laggy. Like, you forget that there are performance hits to things that you build, and if you throw on, say, you're in SwiftUI land, and you throw on too many view modifiers, eventually you get to a point where, or if you use the wrong one, Swift UI performance really starts taking a hit. You drop frames, your phone warms up, it's not a fun time. And the reason behind that is behind each of those modifiers, like say you're animating a view, you're rotating it, you're scaling it up, behind each of those is a calculation. That's what iOS is doing under the hood here. It's doing a calculation for every point in your view's layer to see where that view should actually render at that point in time. iPhones are super fast nowadays, but if you do enough to it, it will still slow down. So we'll be taking a look at these calculations today, and I don't expect, like the goal for this isn't for people to understand how the math works. I probably don't understand how the math works, but I'm showing it to you in the spirit that if nothing else today, you gain an appreciation for how much goes into some of these seemingly basic calls, like the Swift UI. Dot rotation 3D effect takes a few arguments, rotates your view so it looks like it's moving in 3D space. Super awesome. The code looks clean. You're happy. But there's actually a lot of math that goes into it. And hopefully, you guys can appreciate the intensity of some of these calculations and just start to think about them a little more conservatively. Don't just use them willy-nilly as you start to build some really, really amazing user experiences. So the most basic of matrices that I can think of just as a starting point is what's known as the identity matrix. This is the way that Apple represents it in their documentation, just 4 ones there surrounded by zeros. The reason I had crisis striked out there, the effect of applying this onto your view should be nothing. This is the exact same as multiplying a number by 1. Literally, you're multiplying by ones. Your view will stay in place and do nothing if you try to apply this as a transform, because it's just saying, like, hey, rotate this by nothing, or like scale this up by nothing. So you might have noticed, well, why are there 4 ones? Why are there 4 rows and 4 columns? We just spent all that time talking about 3D space. The heck did the 4 come from? Well, there's a reason behind that. It's actually needed for the math to work out for translations. And we'll ease into things by looking at translations now, just to give you an idea of why there's 4 dimensions, and also to just try and learn how this kind of math works as best we can here. So this, again, is provided by Apple. It's in their documentations for a CA transform 3D make translation. Yeah. CA transform 3D make translation, CA transform 3D translate. Anyway, this is the matrix that they say gets applied to every single point in your UI view, or Swift UI view, when you try and move it around the screen. So say you had a box on your screen, and you added a tap gesture recognizer to it. And you want the user to be able to drag it around. That's just purely moving it around on the screen. You can do all that without digging into the low-level APIs we're talking about, but under the hood, this is still what's going on. So there's only 3 variables here, which makes sense when you think about it. All we want to do is just kind of move in either the X direction, the Y direction, or the Z direction, so in and out of the screen in the app. And so that's what you see here. And taking it back to our question here of why are there 4 when there's only 3 things we have to worry about, it does need to be 4. And the way to make this work, if you've done the math before, you'll know, but we need to have an extra 4th dimension here. And the best way we can do that without affecting anything is not make it a variable, make it a number. And what's the easiest number we can throw in that won't do anything? Like we just talked about, the identity matrix is just a 1. And so that's what Apple does too. We'll just throw a 1 at the bottom, and that just makes all of these calculations work without actually impacting anything in the end. OK, so how does this actually happen? How do we get from this nasty-looking garbage to our new coordinate? Well, bear with me. It's a little bit of math. We just got to multiply, essentially, our original coordinate by every single column there. And we do that basically just by drawing a straight line across. So x times 1 is x, y times 0 is 0, so on and so forth. And that's it. Wasn't too bad, right? We just got to do that for the rest of them. And great, now we have even more numbers. What the hell do we do now? All that's left to do now is sum them up. So x plus 0 plus 0 plus tx, and et cetera for the rest of the columns. And what does that give us? Well, that gives us our new coordinate. And you can see how those values in that matrix that Apple defined end up being the exact translation that applies to our coordinate in our view. Your view will be shifted left or right by that tx. It'll move up or down by that ty. And it'll come into or out of the screen by that tz. As for that 1, well, we threw it in. It didn't do anything. We don't have any nasty numbers. It still stayed as a 1 at the end. So what iOS does and what we can do here, forget about it. And it just dies. And that is our final coordinate. And that was translation. So that wasn't that bad, right? We got through it together, still in one piece. Cool. So I promised that we'd look at bits and pieces of that dev tool I made. We'll just do that briefly now. This is how translations work in the dev tool I created. So you can see that I do have a gesture recognizer here, but what I have done is just directly apply this as that matrix instead of doing any kind of constraint adjustment or frame calculation there. And I'm just moving in the x and y directions here. I don't know how easy it is to see, but I added the little matrix here. I'm sorry about the quality of the graphics. I did this at an ungodly time last night, as you can see by the timestamp there. Very prepared, very, very Apple. But yeah, it's neat how you can see how, yeah, there's definitely easier ways of doing this, but even if you were to use those ways, under the hood, it's still doing all of this stuff as well. And if you're willing to reach down into the lower level APIs, you can get that exact same effect too. And the next easiest kind of 3D transform to talk about, I feel like, is scaling. Because if you want to scale a number up in general anyway, like 5, you want to make it 5 times bigger, you multiply it by 5 again. You just multiply something by the number you want it to grow. And what does this mean in matrix land? Well, this is Apple's representation of scaling a view up. You would scale it up by SX, so it gets bigger in the X direction, left, right. It would get bigger, or get taller, sorry, in the Y direction by SY. Z is kind of tricky to think about as a concept, but if it had like a 3D depth, it would get deeper by SZ. And the one there, like we said, is just for the math to work out in case you also wanted to do a translation. And if you're doing it by hand, you might think, well, in case, why do I need an in case? If I'm doing a scale, I'll do a scale. Again, this goes back to the idea of those higher level APIs where you can very easily just decide to combine multiple things to make one smooth animation or one smooth transition for your users. And so this always has to be in place at iOS, and iOS will always check for that and make sure it's safe by having that extra row in there. So I won't show you the math again, but if you were to do the multiplication like we just did, and that was safe enough for us to figure out together, you'll find out that the coordinates do work out. Again, we can drop the 1, and the transform does end up being applied to every single coordinate in our view as expected. And we can see again a quick example of that in the design reviewer. I added a pinch gesture recognizer. I read the value of it when it changed, and I just applied it through the matrix as well. Crappy matrix rendered in the corner there again. And yeah, OK, that's 2/3 of the transformations that I wanted to talk about today. And we haven't died through the math yet, so that's a plus. But the next one is where things get a little muddy, though, unfortunately. We're talking about rotations as a final one. And rotations means trigonometry, and that's not fun at all. When you get to rotating in 3D space, if you just have a point and you want to rotate it in an orb anywhere arbitrarily on the screen, it gets really hard to keep track just visually, let alone mathematically. So to help simplify, we'll just rotate around one axis at a time, meaning I'm not going to let the user rotate in the x direction. I'm just going to let them rotate in the other two. I'm not going to let them rotate in the y direction, and so on. And that simplifies our thinking and keeps the math relatively simpler for the time being. To keep it light, don't worry, I won't show you the full thing. Like all 3 axes, I'll show you one of them, and I won't dive into the math too much because I'd fall asleep too. It'll be on the screen, but we won't have to talk through it all, don't worry. So let's say you had a point on your view that was just somewhere out in space here. We'll hold the x-axis constant, so we're looking at rotating in the z direction on your screen, so again, coming into or out of the screen, or rotating upwards on your screen or downwards. And let's say it's out there in space at some point P, and let's say, hey, I want to move that view a little higher up, shift it a little further up to some new point. I'll call it P prime here. How do we describe getting from point A to point B, point P to P prime? So that's where triangles would start to come into play. And I'll pop them out to make it a little more explicit that it's about to get really toxic. So you can see here that your point P itself is already rotated relative away from z being equal to 0. And point P prime is rotated even more, not just by that original alpha, but by some additional angle of beta. Our goal here is we'd want to describe our new point in terms of the original point. Because if you think about those transforms we just did, that's the same thing. We want to be able to describe our final target by that original form. We don't need to worry about the extra fluff. So like that R that I wrote there, that doesn't really mean anything in iOS land. If we really had to give it a definition on this screen, here on the slide here, it would be the distance from the top left of your screen to that location on your view. Doesn't really do anything. We don't want it to be in our final description because there's no API for it. There's nothing we can do about it. And it's trigonometry, man. It's using everything we hated from GCSE, from high school. I can talk about it really briefly. You're basically applying those fractions at the bottom there to each of those triangles at the top and just seeing what comes out. So you can see we already have most of what we want here. We have our new final coordinates, those z prime and y prime there on the far right. You can see that right now, though, they're being described in terms of that value we don't want. We want to get rid of that. So we have these equations. How do we get rid of that r and end up back with only the original point? And another thing you might notice, it's scratching some dark recess in your mind that you hope to never scratch again, is that those two far right formulas, isn't that trigonometry too? Yeah, it is. It's the kind of stuff you instantly, like you write on your hand in red ink so it's not as obvious during an exam and you can get away with it. I hope I'm not the only one that did that. And from here on out, it's just a game. Again, the target is you want to get your new coordinates in terms of your old coordinates. And every teacher that's ever gone through this with me has always just been like, you just got to be able to tell what to sub in and what to sub out. So we know that our target has to do with those two equations on the right. And we have these two properties on the right up top here. I'll give them additional labels now so they're not just gesturing vaguely on the screen. So we have 3 and 4 that we want to work with, like we said before. And we've just gained 5 and 6. So we can sub 5 into 3. And you guys all know the story here. We're just basically subbing things in. Z prime equals to r times whatever the cosine is. We've brought 5 into that one. And now you can see that r is multiplied throughout. But then we notice that, hey, that giant mess there, that r cos alpha, well, that's just our original z. We know that from equation 1. And our sine alpha is just y. We know that from equation 2. And that's already it. That's done. That's our final coordinate, z prime, described purely by z and y, our original points. And if you apply that same logic, I'm not going to bore you with it a second time, you end up with y prime, described in the same way. And that's it. Managed to get it over in 2 slides. And the very last step is just turning it back into a matrix. Again, this is just trial and error. We learned how to multiply matrices before. This is just a matter of making the math, moving the terms around until that multiplication gives us the formulas that we wanted. But remember, we did hold x constant before. We said we were going to ignore it. So we can bring it back just with the same idea that we had with 1 earlier. We'll just slap a 1 onto the matrix where the x would have been. But we do also still need that 4th dimension, too. And that, finally, is what Apple defines as a transformation matrix for rotation about the x-axis. They do that 2 more times for the y-axis and z-axis. I would hurl myself off the stage right now if I tried to do that myself, so we won't bore you with that. but I can show you visually what that looks like in the design reviewer again. Nice boring ass animation there. I'm basically dragging that view around in space, and it's only rotating about this one fixed x value. You can see it's not moving left or right at all. I'm just purely rotating around there. And yeah, that's just me taking the amount that I want to rotate by, so some angle, and I'm just changing that over time with my finger, feeding that through into the matrix, and it's just making the animation happen. There's not any complicated math. This is just for visual purposes. So we now know that for any kind of transformation you want to do in iOS, it's just a multiplication at the end of the day. iOS will take your coordinate, x, y, z, and multiply it by whatever matrix you define. And Apple does provide, like we've talked about, the rotation matrix, the translation matrix, as like readily available APIs. But at the end of the day, you could build this yourself if you wanted to. If you got a reference to that translation matrix, you could still call matrix.m14 and change that value to whatever you want. And the behavior of that gets messy, and that's where understanding things like this come in, where you know what the impact of that will be. And for the most part, you would never need to dive into that level. But if you were to dive into that level and make those random changes, then the only added caveat is you can't rely on that 1 always staying as a 1 at the end. It could be like, say it was like 10 or 50. There's one very last step that iOS will do. It'll always divide by that value first. So if it was 50, it would say like, okay, x over 50, y over 50, z over 50, 50 over 50. And that would get you back to 50 over 50 is 1. And so then you can drop the 1 after that, and that would be your final coordinate system. That's called normalization. We don't have to worry about that, just an FYI. So you can apply one transform at a time if you wanted to, but honestly, why would you, right? Like if you're doing a translation, like who the hell would do what I just did and use a matrix for that, right? You just hook up, if you're in Swift UI, you can just hook it up to some state variable, right, some observed property, and it just moves around when you tap it, right? Like you'd never need to know this in your life. The only reason that this starts to become relevant, or at least worthy of your consideration, is when you start getting into compounding all of these different animations and gesture recognizers together, you know? Like what I just showed you was, I had like this design reviewer doesn't seem, just skip through these. This doesn't seem super useful in itself, it's just rotating in space. But it becomes a lot more powerful when you can start to combine all 3 of the snippets I just showed you at once, right? You want to be able to let the user move around on the screen, zoom in, and rotate, and not have the view reset every time you touch it just because you're only letting them do one of those things at a time. You want to be able to do all those things at once, either in response to user feedback like this, or say a view on a peer or view controller view did load. You want something fancy to happen on the screen. You know, maybe you get a Figma mock that says like, this view appears out of nowhere and gets hand-drawn over time and gets bigger as time goes on. And the best way to do that, again, you can use those higher level APIs, and for the most part, you could be totally fine with it. But the more complicated that starts to get, it's definitely worth appreciating all of the work that goes into each of these transformations, because that is pretty computationally intensive, less common of a problem now with our awesome iPhones today, but you can't just always design for like the iPhone 50 and that's out now, right? You always got to keep in mind, hey, what's the oldest iPhone that supports iOS 17 this year? Was it the 10R? Was it the 11? I should probably know this, shouldn't I? That's still a super powerful phone too, but you know, like older hardware won't perform nearly as well as newer hardware. And if you try and do a bunch of SwiftUI folks like geometry readers nested into each other, that starts to take heavy performance implications very quickly. And this is the reason, all the math that goes into the work that goes in behind the scenes. And sometimes it is worth just doing it by hand like this, applying these transformations at this sort of API level, because then you know for sure that this is the only thing that's happening at that point in time. iOS is probably doing a bunch of other stuff when you call, say, UI view, like if you get an animation block on UI, did I just say block? I think I just dated myself there. That's Objective-C. An animation like closure to wrap around, like say 4 or 5 property changes on a UI view. So I want my UI view to move up, I want it to rotate down, You can do all of that with a high-level API, but without accessing these transformations by hand, you kind of take for granted that all this math goes into the scenes there. So doing it at this level like this sometimes just makes more sense. It did for me personally. The math was just because I hate myself, but applying these APIs directly made more sense for me from a performance point of view. At the time, I think my work phone was an iPhone 8, and so trying to get those animations working smoothly was not fun, almost as bad as actually using Xcode, so it wasn't really worth it then. But I've been talking a lot about putting all of those things together, so I'll show you quickly what that looks like. And so you can see I was able to get, at least I hope, kind of close to what that Xcode UI looks like. You can see I'm able to zoom in and out. I've been moving it around. I can rotate it in 3D space. And that's all thanks to me just taking essentially a screenshot of the view and just applying those transformation matrices every time the user taps on the screen, every time they zoom in, every time they rotate around. And you can see the code for it on the right here. And I've open sourced this all on GitHub, so it's readily available. No need to take pictures. It's not that verbose, right? There's not that many lines of code to make all of this happen once you get past the fact that this is ridiculously low level and involves math. It's actually, in code itself, it actually doesn't look that bad, right? Just a few lines that let you create this effect on a UI view. So these are explained in way more depth than even I would ever need to know. Up on my website, I posted a couple write-ups about this. alexlee.zip, because signing up for a new top-level domain is the only way in hell someone with my first name, last name can get first name, last name, dot anything without like an obscene number at the end. I was telling some of the people earlier, I joined Apple and I think I had like 56 on my email, which is just great. They were like, oh yeah, why don't you just add the word Siri onto your, okay, we're good, onto your name so that people know it's you. And I'm like, there's still like 20 others in there. Like, it's not going to make a difference. It's a lost cause. I digress again. Those write-ups are available on my site. There's also a second article on there about one value that Apple does tell you about. You see that M34 there near the bottom right-hand corner? Apple actually recommends, without explaining at all, ever, why they recommend it, if you want to modify a view to make it look like it's coming into or out of the screen, like say you had like an arrow, and you want to make it look like it's pointing into the page off at something, they recommend modifying that property and that property only. And they just say, just trust me, bro, it'll work. You know? I thought there had to be a reason why, and I hate myself as I will keep reinforcing. So I figured out the reason why and posted a write-up about it. It's way too much math. But that's up there if you're curious as well. And I kept referring to the fact that these matrices are defined by Apple. They're not actually all on documentation.apple.com. They're still public, they're just not there anymore because the API is so dated that they didn't deprecate it, but they just don't host it up there anymore. But it's up on their documentation archive, so if you just Google Apple Documentation Archive and look under core animation, you can see there that all those matrices that I just talked about are there. No proofs or no explanations, by the way, just there. And yeah, so if you tie those things together back with my write-ups, hopefully you can get a better understanding of how all this works under the hood. Like I said before, the source code for that tooling I wrote, like literally everything there is available and open sourced. If you're interested in seeing how this gets applied and how some of these higher level animations that we take for granted actually work when you try and implement them at the lower level, that's all available for you as well. But other than that, we made it. All right, 8 minutes to spare. Ready for that coffee break, but I guess Adam's got to run a little Q&A session first. So thanks, guys.